visitors from Berkeley, where he's an assistant professor. Aaron was a postdoc at Berkeley. Before that, he was a grad student at Berkeley for a while, as also done an RCVO for 2 years. So, well, I'll let Aaron get started.
All right, well, thank you for inviting me up to talk to you guys. I was going to talk today about some of the progress we've made with the paper project, and maybe kind of broaden it out a little bit, talk about some of the principles of 21 centimeter intensity mapping and how we hope to use that to measure baryonic acoustic oscillations, detect the epoch of ionization. I won't talk too much about it, but there's also a third epoch in there, the dark ages, that's accessible. And I want to, so this is kind of broadly a principle of kind of cheap antennas, paper clips, and using supercomputers to correlate all the signals from these antennas, and trying to build a low-frequency radio cosmology program out of that. And I want to be sure that I highlighted some of the, a lot of this work was done by my excellent student, Jonathan Coker, who made coincidentally be applying for his position to just FYI. I should give attribution for the paperclip. My former advisor, Don Backer, who led the paper experiment, passed away 2 years ago, is credited with saying, all you need to detect the epoch of ionization are paperclips and a supercomputer. And that's the origin of the name paper, our project, the precision array to probe the epoch of ionization. So I thought I'd start with kind of putting things in context of low-frequency radio astronomy that's been conducted. And I've decided to define low frequency as below a gigahertz. And broke it up into a few epochs here through time. It's kind of interesting. I hadn't really heard much about the history of radio astronomy. And so I did a little research here. Correct me if I'm wrong, if you catch me on anything. I hate to be wrong on these things. But of course, there's the pioneering efforts of Karl Jansky and Grote Reber, starting at 20.5 megahertz, 1932, discovering radio emission from off the planet. And Grote Reber followed up on that in his backyard at 160 megahertz. My understanding is he actually started at quite a bit higher in frequency and didn't see anything and kept working his way down until he finally hit the galactic synchrotron at 160 megahertz. He detected that in 1937. So this is the age of the pioneers in 1930s. And 15 years went by, predictably, with the war. And then in the post-war, in the 1950s, we had a whole slew of new radio telescopes show up, which were driven by the technology that was developed in World War II, all the radar, finding a more peaceful application of that. A lot of this was done down in Australia. And I always like these pictures because you're always tempted to look, your eye just is drawn to the dishes in the background, but those aren't the radio telescopes we're talking about here. They're actually what you're thinking are the power lines, or the actual low-frequency radio telescopes here. And then there's kind of the age of discovery in radio astronomy, where you get pulsars are detected, get a whole slew of new but more kind of refined instruments being built, with DARO up there as well, the Northern Cross. And a lot of these, data from a lot of these telescopes are still relevant now for radio astronomy at these low frequencies. And then in the 70s, you have the dawn of computers, and so you start seeing things, instead of having, you have some of the really largest dishes, but you also see them starting to be broken up into sub-dishes that you then use computers to cross-correlate. And this is kind of the dawn of synthesis imaging. And certainly, a lot of the, both from the 60s and the 70s, are a lot of the work that we're now drawing on today to try to do low frequency. And part of that is because we have another 15-year gap where no telescope targeting anything below a gigahertz was built. So you might ask, well, why was that? Well, a lot of it had to do with the discovery of the 21 centimeter transition at 1.4 gigahertz. within our galaxy as a way to map neutral hydrogen. And so it's not that nothing was happening in radio astronomy, it's just a lot of effort was directed towards following that, the 21 centimeter line. And there's kind of a confluence of several factors besides just 21 centimeter that made that very appealing. One was your ability to calibrate your instrument. At really low frequencies, you're limited by the ionospheric diffraction of the sky itself, which for self-calibration you rely on. And so you get phase errors in your calibration that increase as you go lower and lower in frequency. And then as you go higher and higher in frequency, then you start to be limited by the atmosphere, but also by the length of your cables, because your wavelength is getting shorter and shorter. So you need to calibrate path lengths to a small fraction of your wavelength, and that gets harder and harder the higher you go in frequency. So there's this kind of nice well around the gigahertz that draws people towards that drew people towards the 21 centimeter line, even without the great science that was accessible there. And the other was just to look at what are your sources of noise. And amplifier noise starts dominating at higher frequencies, and you start having to cool your receivers. And that's kind of expensive. So it gets harder to work at higher and higher frequencies. But if you go at lower and lower frequencies, then you stop being dominated by the noise of your amplifiers. You start being dominated by the noise of the sky itself. And everything that enters into your instrument either has to be correlated into your image, or it has to be beaten down as noise out. And so where you stop being dominated by the sky itself, and start you can always reduce the temperature of your system by going up in frequency up until this point, until you need to start building better amplifiers, which gets harder. So that's another thing that pushes you to higher frequencies. So, so in some sense, people were off chasing greener and easier pastures at 1.4 gigahertz. So that 15 years is behind us, and we start getting a couple new low frequency instruments being built. GMRT, of course, which is still in operation in India and doing a lot of great science, and the Mauritius telescope on the island of the Dodo were both built targeting bands well below a gigahertz. And my interpretation of these is actually developing countries wanting to make an investment in science, and that low-frequency radio astronomy being a relatively cheap way at this point, because computers have gotten so powerful and therefore so cheap per computing power to just build these instruments. And so cheap computing starts drawing people back into low-frequency radio astronomy. And then this gives birth, with kind of some new attention and with the technology to do it with, to a new slew of science applications at low frequency. Al Rogers detected deuterium at 327 megahertz with a custom-built array. And then I throw in the ATA here. It worked over a very wide bandwidth, up to 10 gigahertz, but it did operate below 1 gigahertz. We have 21 CMA/PAST in China with a whole array of Yagi antennas. And I'll throw in another here. This is the EDGES experiment targeting randomization with the global experiment. And I'll talk a little bit about the signal that's being targeted there. This isn't an element of an array. This is the entire experiment. This one.
So I should know this, but can you give the update on what's happening? I have not seen the 21 CMA initials for PAST. What's the status of PAST these days?
I'm not sure that I'm the most qualified to give an answer. There might, yeah, maybe Willie. Do you want to say it?
I mean, I was in Beijing a few months ago, and they claim that they have made the data public, actually. So I don't think one can download the data.
Okay. I haven't heard a lot, I think is the answer. And so now I would argue that we find ourselves in a bit of a golden age in radio astronomy, where we have some really great science applications, notably the 21 centimeter transition, which has jumped out of the 1.4 gigahertz band And we started doing it at high redshift so that we can trace that transition through the history of the universe. And we have telescopes being designed targeting that. There's LOFAR up in the Netherlands, the MWA in Australia, using tiles. We have the long wavelength array, LWA, in New Mexico, which is being applied to an experiment to measure the dark ages, which is kind of redshifts 20 and higher. And then, of course, there's the project that I'm leading, Paper, which we have 64 antennas in South Africa. And of course, I'll talk a bit more about that. So I argue we're in a bit of a golden age. And why is that? Well, the old way that you would use a radio telescope is you go out to a dish, and it's a dish. You have some real-time signal processing in the form of analog electronics there. You're there observing, you're back in computing, a little facetiously as a writing desk. But in a modern telescope, you have many simple dishes. They're deployed kind of by themselves in the middle of a desert. We have these digital supercomputers that are combining the signals of all those antennas. And we basically tie the capability of these radio telescopes to the capability of the electronics in your signal processing engine there in the telescope. So you've coupled the power of radio astronomy to the power of consumer electronics, which are doubling every 18 months or so, according to Moore's law. Observing happens autonomously, so I'm throwing a sledgehammer to entertain myself once everything is working. It still remains at the highest data throughput to get your data out of your telescope to a cluster where you can analyze it is tapes on an airplane. Although I'll tell you at the end, we've made a little progress in being able to compress our data enough that we can stream a good portion of it out in real time. We've got 100 terabytes of data sitting on a disk and are waiting our way through that. So one of the truths of, now that the capability of a radio telescope is tied to the capabilities of electronics, is that a lot of astronomers find themselves wanting to build new improved backends for their telescopes, or to build new telescopes around the signal processing. And so we find ourselves, especially when the capabilities are doubling every 18 months, you find yourself wanting to do this fairly often and maybe even repeatedly for an instrument. And so part of what we've done with Paper, along with a project called CASPER, the Collaboration for Astronomy Signal Processing and Electronics Research, is to build kind of commodity engines that can be applied to a lot of different applications, built around field programmable gate array processors and also now graphics processing units, GPUs. And we have hundreds of collaborators around the world now who are all using these electronics for their own telescope, including some of the competitors to the Paper experiment. But sharing is okay. And I think another one of the truths looking forward in radio astronomy is with capabilities doubling every 18 months or so, you find yourself wanting to balance the need to get science done now. So you have costs of your telescope, and you'd like to build as big an array as you could. So you want to build lots of antennas, but then the costs of correlate on them, you have to pair every antenna with every other antenna, so that it goes as the square of the number of antennas. So if you're on a log-log plot, I've drawn costing curves for the Paper telescope, where we have n squared, the contribution of the n squared term, which is all the pairs of antennas, compared to the n term here, which is just the cost of metal, of amplifier chains, and some of the processing that goes linearly with each antenna element. And the idea is that because all of the n squared processing is in digital, which with cost decaying exponentially with a half-life of 18 months, that you don't want to build a telescope that's too dominated by an n squared term, because you could just wait 2 years and then build it for half the cost. And so the idea, but at the same time, how do you ever build anything? You gotta get some science done now. And so what we've been trying to do with Paper, and I think is a good approach, is to build towards the need. of these things, where you pick a knee between where your n and n squared terms meet. You build a telescope there with the idea that you're actually going to just throw out the back end of that telescope, double the size of your array, and build a new one some number of years later with new electronics. And following this, it only raises the absolute cost of your system slightly above kind of the optimal if you waited the whole time and then built your array at the end. It only raises the cost a slight amount, and you get to do science the whole way through, which is nice. So now I'm going to switch gears and talk a bit about the science that we're all chasing here. Of course, there's in the beginning the Big Bang. We have recombination, and this is the epoch at which the cosmic microwave background decouples. And then we have a period known as the Dark Ages, where there really weren't very many luminous sources around, hardly any, until the first structures collapse under gravity and form the first massive halos that emit ionizing radiation. So until the first stars light up, we have very little that is modifying the temperature of the intergalactic medium here. And I'm not going to talk much about this period of Dark Ages, but because the hydrogen in the intergalactic medium doesn't have much to interact with, it ends up being pulled alternately, depending on which mechanisms are dominating the spin temperature of hydrogen at the time. It gets pulled alternately to the gas temperature of that hydrogen or to the cosmic microwave background. And there's an epoch where there's a contrast between this hydrogen, the 21 centimeter, and the cosmic microwave background, where you can hope to detect the 21 centimeter signal in contrast. But then your first ionizing sources turn on, and you start getting these bubbles of ionization, where of course you get no 21 centimeter signal when there's no neutral hydrogen there to emit that signal. And this is the epoch that Paper is trying to detect up through to the complete ionization of the intergalactic medium. And then there's a later time here where all the neutral hydrogen is now buried inside the galaxies themselves. And you can hope to measure the distribution of galaxies integrated on the sky via the neutral hydrogen that's in them, and measure their distribution. And of course, the science application of that is the measuring the baryon acoustic oscillations that were imprinted in their distribution to measure the stretching of the universe. So let me see if I can get this to play here. So here's a simulation looking at a cube of space through cosmic evolution as seen through the Lyman alpha transition of neutral hydrogen. And you'll see these cavities forming where we're ionizing out that hydrogen, with the ionizing sources along these filaments underneath. And the problem, of course, you can see is you don't get much picture of what's going on inside of here. You only see the occasional place where these cavities are hitting the edge of our box. But it's not until the very end here where you finally start being able to see a significant depth into this cube to see what's going on inside of it. And of course, at the very end, you get a very interesting signal where you get the last vestiges of the hydrogen ionizing out there. So one of the limitations of using Lyman alpha, which is one of the traditional techniques for finding high redshift galaxies, is that it hits opacity very quickly. And that's a difficult problem to work around, and fundamentally limits your ability to look in a lot of directions on the sky. In contrast, the 21 centimeter transition is a very weak transition. It takes a lot of hydrogen to hit opacity at 21 centimeter. On average, a neutral hydrogen that's excited in the 21 centimeter transition takes 1 million years to decay by itself. And so now, instead of seeing this opaque box, it's translucent at all times, and we just see the varying degrees of translucency. And then, of course, because this is line emission, it starts out at 21 centimeters, but it stretches with the universe as it flows out towards us. And so we can use different frequencies to look back to different times in the past and measure the universe as it was there. So the advantage of the 21 centimeter line, as you can see it at every epoch, versus frequency. The disadvantage is that it's a very faint signal. It's precisely the faintness that prevents it from hitting opacity. But for the paper experiment, I've taken an EOR simulation over a band from 100 to 200 megahertz and multiplied it by 1,000. And that's these pink dots on here. And this is all sitting on an enormous curve, which is our foregrounds coming primarily from synchrotron emission in the local universe. And so you're trying to pick out this little hair on the slopes of Mount Everest. And so this is the struggle that any 21 centimeter intensity mapping experiment is trying to solve. And in various experiments are taking different approaches to managing attaining the sensitivity you need to actually be able to detect the signal, and to try to mitigate systematics that come from the foreground emission that you have to see through, which is predominantly smooth in frequency, and it's that smoothness that differentiates it from the signal that you would hope to measure at just the 21 centimeter line. But you nonetheless have to remove that foreground emission. And so there are various ways of trying to, we have cases of experiments that are optimized more towards sensitivity, where you have large collecting areas where you can collect a lot of signal. And then you have, on the reverse, you have the experiments that have relatively little collecting area, but have been tuned more towards trying to have smooth frequency responses that can enable you to differentiate, to model your foregrounds and remove them on the basis of that. So I've kind of already broadly divided up these epochs into the dark ages, which I'm not going to talk a lot about, but at Berkeley we are involved in the LIDA project using the LWA to try to measure via a global temperature experiment, measure the temperature of the gas in the soil epoch. We have paper, which is tuned towards the epoch of reionization, and we have another project that I'm going to talk to at the end here called BAOBAB, that we're hoping to target the BAO science in the relatively later.
So can we go to the dark ages for a minute? So when you attempt to forecast signals, it is something that you can pick up, or does it require a lot of anomaly?
Well, the difficulty with the dark ages, so the predominant source of noise in any of these measurements is the galactic synchrotron, which is rising with an exponent of frequency to the 2.5 as you go lower in frequency, which is higher redshift. So it's very noisy out in the dark ages. And it's going to be very difficult to do anything like intensity mapping, where you're actually measuring structures or the distribution of structures there. What you can hope is to try to measure the absolute temperature of the gas back then, because that's something, instead of in kind of observable units of microkelvin, it's more like hundreds of millikelvin that you could hope to get. So building an experiment that has the sensitivity to measure the global experiment, the global signal, which is everywhere on the sky, is fairly trivial. Again, it's foreground management that's hard in the dark ages. And it would be a much future instrument that could hope to do anything like 21 centimeter intensity mapping at those frequencies, SKA or beyond. And so finally, I'm now going to talk about paper and where we're getting. And just a brief history of paper. It began in 2003 as it was an idea conceived by Don Backer and Rich Bradley. We built our first several arrays in green bank, PGB being paper in green bank. A nice 4 antenna system where we're kind of getting our bearings. It had no flaps back then, our dipole elements. And we've eventually upgraded those to have flaps to narrow our beam. I joined the project shortly thereafter as a student, and then since then, with a couple of hiccups, but we've basically been doubling the size of our array every year. So this is again building to that need of what's cheap and easy with current technology. And And we had a first deployment in Western Australia, but since then we've actually switched to being in South Africa. And that's where our primary science deployment is now. Green Bank has 32 antennas, and that's all it's ever going to have, at least as currently spec. But in South Africa, we're continuing to build out our array. We currently have 64 of our elements out there in the field in South Africa, and we're going to, by this time next year, have 128 out there. So we have a couple different.
What does times 2 mean?
So when you have, say, 32 antennas, each of these are dual polarization. So you can have a choice of correlating all the polarizations of each element, or you could just into your correlator hook up one polarization from each antenna element and get more samples of the UV plane, but you get no polarization information there. And so we've alternately been using these deployments where we use these single pole observations of 32 or 64, and then we can switch the same correlator to use 32 dual polarization observations. So we have these observations in hand. We're currently, we've been operating for a month now, taking 64 antenna dual polarization observations. And then next year we will begin our 128 element dual polarization observations. We can move paper antennas around, and we use different antenna configurations for different science goals. So here's an example of scattering antennas around in a field in what looks like a haphazard, random way, but it's actually optimized such that every pair of antennas, the separation of them, gives you a Fourier mode of the sky that you measure. And this is optimized such that every pair of antennas has a different separation, so that you can sample as many different Fourier modes of the sky, which allows you to make images with very low side lobes. You can make very nice pictures of the sky with this. And so we call these our imaging configurations. And here's a picture of our 64 antennas in South Africa in a minimum redundancy, so a imaging configuration. It's a backhoe picture for scale. And these allow us to make nice pictures, although the luminosity of the projector isn't great here. This is the galactic plane here. Great. You can turn that on in just a minute. This is Centaurus A with giant lobes jetting out there. Here's a nice supernova remnant where you see the shell of it, where you're seeing through a lot of the ionized gas on the shell of it. And then this is the galactic plane. And the way we've laid out our antennas, we have very little information about the broad scale of the sky. So this is kind of a high-pass filter placed on the sky. And what you see are all the supernova remnants dotted in the galactic plane. So we can make very nice pictures of the sky there with this. And if we can catch the light back on. And then I wanted to highlight this paper that actually just came out on the archive today of grad student Irina Stefan, who made images of Centaurus A, which was that structure I showed you up there, and then characterized the spectral index of the lobes to measure the magnetic field in that area. And so these are all great for making pretty pictures of the sky. But fundamentally, every measurement that an interferometer makes, there's the UV plane, which is the Fourier transform of the sky, the angle on the sky. And then you have the frequency axis. And interferometers sample this volume of UV and frequency. And every single measurement is corrupted by foregrounds to the reionization signal. And so red is kind of attempting to illustrate foreground images. And when you take an image, you take the Fourier transform of the U and V coordinates, but you can still preserve the frequency direction. And you get coherent structures on the sky at some location versus frequency. And this is great for making pretty pictures of the sky. But if you want to measure reionization, our best statistical probe of that right now is is through the three-dimensional power spectrum. And so since U and V are already Fourier transforms of the sky, what you really would like to do is take the Fourier transform of the frequency direction, which was a distance along the line of sight, to get inverse frequency. And this is a volume that corresponds to the three-dimensional Fourier transform of a volume out there at redshift 10. And if we have smooth foregrounds, like we expect we have, then all of these measurements should be confined to a low-order modes in this inverse frequency axis. And we could hope in this gray area to detect reionization. And so imaging and power spectrum sensitivity are fundamentally different ways of using your data. And a configuration that works for imaging, optimized for reducing the side lobes in angular space, doesn't necessarily help you with suppressing your foregrounds by confining them at low-order frequency modes. And moreover, because we care about particular Fourier modes, especially for a sensitivity-starved experiment like paper, what we'd like to do is to get our sensitivity is best used by measuring the same modes over and over again until we get about signal-to-noise of unity in any one of those modes. So what we use for our power spectrum measurements are these configurations of antennas all in a line. And I should point out that there's a dramatically different scale, east-west versus north-south on this. These essentially look like antennas close packed together in a line with broad spaces between them, such that you get a lot of repeated measurements of the same separation over and over and over again, which means in the UV plane, you're hitting a particular mode here with a whole bunch of the same measurements. And that helps you build up sensitivity faster on particular modes. And so when we were ready to do measurements where we try to constrain the power spectrum of reionization, we move our antennas into these redundant configurations here, which you can see across the middle of the array. So this is the 32 dual polarization observations that we ran last year and are analyzing right now. All right, so I want to talk a little bit more about those foregrounds since we have two battles to fight. One is to get the sensitivity, and we have some help by using these redundant configurations for power spectrum measurements. But the other is we have to constrain our foregrounds. And part of the problem is that even though our sources themselves may be spectrally smooth, they have smooth spectrum versus frequency, our instrument itself introduces structure onto that signal. And one way of thinking of this is the Fourier transform of frequency is time. Right? So what time is it? The time that this ideally would just be the Fourier transform of this spectrum. But what convolves that signal is the time lag between when a signal from a source hits one antenna and then hits the other. And so if this source were straight up and coming down, it would hit these antennas at the same time. And so you'd see the Fourier transform of the spectrum of that source at delay of 0. But for different directions on the sky, you get a different amount of delay from when that wavefront hits one antenna to another. And it can be positive or it can be negative. And so if you watch versus time, you can actually pick particular sources and watch them walk around on the sky. This is just a simulation. But you watch them walk around on the sky. And for smooth spectrum sources, you can see that the emission from that source is relatively confined in this, what we call the delay spectrum, the Fourier transform of the frequency visibility measured by the antenna. But if you put in a source here that has a lot of structure on it that is not a smooth spectrum, you'll see that even though the center part of that source follows that same trajectory, it's got these wings to it that show all of the structure that this spectrum had. And actually, this is something good for us. Reionization is not smooth. One could hope that reionization were unsmooth enough that it could have lobes that spill out over well beyond the region over which these sources track back and forth. And that's actually the key to detecting reionization. One can directly interpret these delay modes as K modes, as the three-dimensional measurements of the three-dimensional power spectrum of ionization. The only problem is that these foregrounds kind of systematically corrupt some number of low-order modes. And what we'd like to do is confine these foregrounds to as narrow region as possible. So what determines how far out in delay these sources can go? Well, if you take a source, if you put it up at zenith, it has no delay relative to these. If you put it over on the horizon, then the maximum delay it could possibly have is the time it takes light to travel from that direction, hit this antenna, and then hit this antenna. So that gives you a clue. Yeah?
Well, have you carried this out successfully with real galactic sources where
Yeah.
doesn't matter?
Yeah. I'll show you some pictures in just a minute. So the idea is if you put your antennas close enough together, you can make that time shorter. And that essentially moves this limit, which I sometimes call the horizon limit, because it's the limit, the maximum delay if you put a source on the horizon, moves it closer in and leaves more of your space accessible here. And you can actually do this as a function of baseline length, which, because its baseline length is also in U and V coordinates as part of the Fourier transform of this three-dimensional cube. I call it K perpendicular here. And we draw a line here. This was done by Jonathan Pober. We draw this line here at where the horizon limit should be and measure for all the baselines in a minimum redundancy configuration. So we have a whole bunch of different baselines. We see that they all basically obey this line, and with a small departure from it that corresponds to the width of the Fourier transform of the spectra of sources that are at the highest delays, that spill over a little bit. And we see that it gets a little worse here at the lowest, at the shortest baselines. And we think that this is actually the brightening of the sky, where we pick up more and more of the broad galactic synchrotron at the lowest spacings. But in this, you can see right off that this is, from here off to the edge of these kernels, is 4 orders of magnitude in temperature squared units. So in temperature units, this is 2 orders of magnitude of suppression. And we can verify that this is noise out here. So to the limits of these measurements, we're noise dominated. Very soon, it's about 15 nanoseconds off the edge of the horizon limit. And so if you take data measured by a baseline versus frequency and versus time, this is amplitude here. And if you take the Fourier transform of the frequency axis, like we just talked about it, you can get delay. And you can watch the sources move back and forth here. And one of the keys is, when all these cross-hatching here is data that we've had to remove. This is green bank data where we have more RFI. But it's interference that we had to cut out of our data. And the problem is, any time you cut data out and you want to do a Fourier transform, you've lost information. You've introduced these sharp discontinuities in your data. So you need to bridge over those with some sort of interpolation, or if you take that Fourier transform with deconvolution. But that's actually a very solvable problem. You can deconvolve out the sampling pattern that you have here and really restrict these sources to the inherent spectra that they have. And then something else you could do, and this was described in a paper in 2009, is you can take a Fourier transform of the time direction as well. And it's a little less clear what that means, but different parts of the sky rotate by at different speeds. And so taking the Fourier transform of the time direction essentially gives you some information about another direction on the sky and where sources are. And you can work out geometrically what these different, for different baseline orientations, what different delay bins correspond to on the sky, and what different fringe rate bins correspond to on the sky. And so by picking out a particular delay and Fourier transform of the time axis, which we call delay rate, you can select different regions of the sky that you'd like to look at. And it turns out this has been really valuable recently in that straight out of the correlator, we sample a whole bunch of frequency channels, like 2,000, And we dump data at 10-second cadence in order to be able to catch all the RFI blips and everything that happens in that data. But if you do this two-dimensional Fourier transform, all your foregrounds are select. We argued there was a fundamental limit as to where foregrounds could be in delay space. There's also a fundamental limit of where they can fall on the sky, just because things that are locked to the sky process around it at a fixed rate. And so you can actually, if you just want to look at foregrounds or only low-order modes of delay and time variability, you can select out a subset of that data to send over that has all the information about every foreground in your system, and actually a lot of information that you can still use to detect low-order EOR modes. And we can get something like a factor of 30 data compression data. So this will enable us to actually stream data out of our telescope out of Africa into our cluster at UPenn in real time, which has been very nice. And so now talking a little bit about a different observation than a power spectrum observation now. And look, you were asking, have you applied this delay filter that throws out data within the horizon limits on a particular baseline and tries to find what's beyond that? We did that with some data from a maximum redundancy configuration, so it's power spectrum configuration. And so our raw data sits up here. This is in millikelvin at a bit over a Kelvin on the sky, measured by this baseline. And then red is if I just straight up difference each frequency channel on that. And I get something like an order of magnitude suppression of my signal. If I difference every time sample, I also get around an order of magnitude suppression of that signal. But this is nowhere near what we need to suppress our signal by in order to detect reionization. But one thing you can do by making these sharp filters in delay space, you can remove most of this. And so here I've applied a filter across a whole 100 megahertz band to try to extract out what I think are foreground-dominated modes and preserve reionization-dominated modes. And this is well over an order of magnitude. And these are noise-dominated. And I can then sum these over multiple baselines and integrate for longer. And we are now sitting at residuals that are mostly noise-dominated. You can see if I difference frequency bins, it suppresses it a little bit, which means there's a little bit of foreground still in there. But basically, these are just slightly, and we don't know what, from this plot, I'll show you in the next plot, where these foregrounds are. Are they modes that are just the next ones out that would be nice if we detected reionization, but maybe can't realistically hope to, or is this some fundamental limit across the whole band? And I'll argue that this is actually just those little outermost modes that mean you have to walk a little farther to higher order modes to detect reionization. But basically, we're very close to noise-dominated signal after integrating this is with 1 month of data from our configuration.
And what is being plotted there? So this is a baseline at what separate with what K and what?
So this is one baseline that's 30 meters east-west.
30 east-west.
But we have 28 samples of the same baseline. So I can go from here, which is with one baseline, but I have 28 samples of that same Fourier mode. And then when I add those 4 different samples of the Fourier mode together, I get this suppression, which is just noise integrated down.
So to get to that above that, you apply the filter, that the lag filter?
Yeah.
On that baseline?
On this baseline, using 100 megahertz of information. Even though for reionization, you want to pick some volume over which the cosmology doesn't change.
And how do you do the conversion to millikelvin?
So these are these are not millikelvin as applied to reionization. This is in raw temperature. There's millikelvin normalized to cosmological volume for power spectrum measurements, and then there's just knowing that your sky is a 300 Kelvin synchrotron emission resolved out by your baseline and then integrated again. you should not interpret these measurements as being
Okay, so that's off, but the filling factor is about 10 to the 4, right?
something like that. What I'll show you the power spectrum plots in a minute. So you can take those residuals and make an image of them. This is this is what a beam looks like on the sky. It's terrible, looks horrible for trying to make pictures of the sky. But it's, it was optimized to preserve the spectral smoothness that we use to discriminate foregrounds. And we get, here now showing in temperature, using all this data, 4 orders of magnitude of suppression of those foregrounds, and being nearly noise dominated at the bottom. And so, this is very preliminary. Please don't quote me on this. We're still working on this. But these are preliminary power spectra from these measurements. Again, it's, I'm not doing a full analysis of this. This is what my student, Jonathan Pober, is going to do, is the full analysis. I'm doing a simple first analysis. 28 redundant baselines, nothing else. There are lots of other baselines in there that we're just not using right now. With 40 days of data, and I'm plotting the 2 sigma upper limit here now in cosmological units of, that can be compared to reionization models. And then the slight departures from noise that we were seeing are these 2 points here with slight shoulders to those. This is the foreground mountain that we're trying to get rid of. And you can see we've got now, in temperature squared units, something like 7 orders of magnitude of suppression of those foregrounds. And then if you walk out off the shoulder of these are now demonstrably noise-dominated samples. So we're still integrating down on those. And 2 sigma upper limit, something on the order of 10,000, which is comparable to the limit that Greg Ziga has set with GMRT. And we're hoping we've got another tenfold of sensitivity in the bag with the data that we currently have. And then, of course, we have observations underway for the next set. So I'm going to skip over that really quick, just in the interest of time. I wanted to mention a new experiment that we're working on, BAOBAB, which is the BAO, so the baryonic acoustic oscillation broadband and broadbeam array. And the idea here is to try to take a cue from the paper experiment and our approaches for removing foregrounds and leverage a lot of the signal processing that we've developed and apply it to a redshift kind of 0.5 to 1.5 or 2 experiment for detecting baryonic acoustic oscillations. And this is all in a paper that Jonathan Pober published that is submitted. It's under review, but it's up on the archive. And I can give you the phone number of it if you would like a bit later. But the idea is that basically you could, with a relatively modest array, kind of 50 elements or so, you could hope to detect the power spectrum of 21 centimeter emission at redshift 0.5 to 1.5 or 2. This isn't measuring baryonic acoustic oscillations, but in a very modest amount of time with a modest number of antennas, getting to the first stage of analysis, which is actually detecting the hydrogen that's out there at redshift 1 to 2. And then you could, with an increase in the size, so bumping up to say 130 antennas, start and observing for kind of 2 years or so. And this is wall clock elapsed time, so 2 observing seasons, where you could place constraints on baryonic acoustic oscillations that are very competitive with what's currently being put out by BOSS. But by using 21 centimeter emission and picking up a lot of information both along the line of sight, using the different frequency channels, and on the sky to differentiate your signal from redshift space distortions. And also moving to higher redshift than are currently accessible by a lot of these current BAO experiments, that we can dramatically improve the constraints that are placed on dark energy and the possible evolution of the dark energy equation of state over what can be done with these optical BAO experiments by themselves. And so, this is very similar to what time could hope to do. And I guess one of the main distinguishing factors that we're
so effective difference, time is got a factor of 10 times smaller error bars.
Factor of 10 smaller error bars on this for the fall time. Yeah. Agreed. But again, similar to kind of some of the trade-offs we discussed in the ethic of reionization, is we're using scaled down versions of the paper dipole. So you have to balance sensitivity and foreground, managing your foregrounds. And similar to what paper's been doing, which we've kind of shown has been a very successful approach, is really putting a lot of stock in the designing your experiment for foreground management and using some of the other tricks, like placing antennas very close together and redundantly measuring the same mode to try to build your sensitivity. And so we built some prototypes of this system. We have 4 of these elements. We've got some low noise amplifiers. We hope to get 50 Kelvin uncooled low noise amplifiers. We're currently about a factor of 2 off of that. We're using all the same signal processing that we use for paper. And we put 4 of these out and we recorded some fringes. And the idea is we would gain 4 of these together into a single element. And then each element, when I say 132 elements, would be 132 of these 2 by 2 BAOBAB elements.
Can you just tell me what is Leuschner Observatory?
Leuschner is an undergraduate observatory that's over the hill in Berkeley. It's just a place that's accessible. It's a terrible RFI environment. We correlated 400 megahertz of bandwidth and found 40 megahertz so we could even see the sun. So clearly we need to pick a better site, but it was a nice demonstration of the signal flowing through the system. So kind of looking forward, for the reionization science, we're hoping to pitch a next generation instrument, HERA, the Hydrogen Epic Reionization Array, that incorporates a lot of the elements and lessons learned out of current generation 21 centimeter reionization experiments looking forward. And we have a pretty nice endorsement from the decadal survey that was conducted in the US for following that path. The 21 centimeter BAO landscape is pretty complex right now with a lot of projects in their early stages. And we may see what happens there. And all of this has to be put in the context of what's happening with the square kilometer array. There's been a site decision to put a low frequency SKA in Australia, a mid and high in South Africa, and how do any of these other efforts interact with the SKA movement is a bit of a conundrum, especially in the United States, where we don't necessarily have backing from our politicians on being involved with the SKA. So I'll just close with the Berkeley Radio Astronomy Lab, where, as I pitched, we're using various types of paper clips along with supercomputers that we keep upgrading, but basically use the similar architectures and similar technology for all of the experiments that we're involved with, and are hoping to field 3 different experiments targeting BAO, EOR, and the dark ages. Thank you.
Okay, so we have time for questions. So Chris?
Regarding HERA, how do you expect the noise level to scale with the size of the array?
Well,
or is that the best, not the best way of phrasing it?
It is a reasonable way of phrasing it. So, kind of naively, you can get a factor, if n is the number of antennas in the array, you can expect your noise to drop as basically n. You can outperform that a little bit, but it's a nice rule of thumb. But then you also have to think about what a single element is. What is each n, each element in that n? For paper, it means a single dipole element. For something like MWA, that's a 16 dipole elements that are all closely packed. And so, what's the best way? You certainly get more sensitivity with the 16 elements, but that can come at a cost of foreground and how those enter your system. And so, I would say we're currently exploring the idea of a hybrid approach where maybe each element could be of a similar design, and maybe without using such a large tile, you could pack a couple of them close together. But there's also some question of, do you need to do that? Can you just throw a lot of digital signal processing at the problem? And I think that's actually a fairly fruitful approach. And so when you get to the idea of building 1,000 antenna or several thousand antenna elements, you need to think about the elegance and simplicity of the system. How do you maintain that many? And it may just be that.
Beyond the fact, can you describe, how far are the reionization models telling you how to go?
So I think, in order of magnitude, 10 millikelvin squared is where we'd like to go. It depends a bit on which K modes you can access. And I think our hope is with the 128 dual polarization, so that the integration that would start a year from now, that year we would be around 100 millikelvin squared at the end.
So, if you, looking at our 800 megahertz format maps, and it only gets worse at lower frequencies, we would conclude that, in fact, for our intensity mappings, the biggest single rate limiting step is polarization leakage. And you have to get to intrinsic. So if you only do lag filtering, you have to get that leakage down to less than 40 dBs across the full primary beam. Is there any hope that these dipoles will have minus 40 dB?
So these definitely do not have polarization leakage that low. We're more around 20 dB, just raw with these. So clearly, we expect to hit our polarization foreground fairly soon, actually. And the hope there is that the thing that's making polarization unsmooth is the fact that, if we could form Stokes' I perfectly, we wouldn't have a problem. But if we are coupling Stokes' Q in there, then that linear polarization gets modulated through rotation measure through these screens, and so it has this frequency dependence that can potentially crush us. An idea we're exploring right now is actually using our full bandwidth to do rotation measure synthesis, which is instead of taking Fourier transforms in linear space frequency bins, binning in wavelength squared, which is the linear measure of how phase is being rotated by these screens, and looking for signals that coherently add through your whole wide bandwidth when you bin them that way. And we're trying to create filters that we can then use to remove those coherently using these 100 megahertz bandwidths, such that we can open up 10 megahertz bandwidths without those modulated signals. And we have to see what kind of suppression we can get from that. We can, through simulations that are being done by David Moore and James Aguirre at UPenn, it looks like it's pretty trivial to get a factor of 10 suppression that way.
Well, point was, for galactic, you get nothing at all, right? Because that's space splitting in ion space.
Because it's
fitting. So the point sources have a well-defined delta function in ion space. So if you just sit down, if you cut them out, you may get rid of them. But galactic foreground, because you have the emission mixed with rotation screen, after you do the Fourier transform, it's still dense. It only helps those gains if you take it back.
The idea is that the delays at which any emission comes into the sky, whether it's diffuse or point source, is limited in delay already. So we're making these two-dimensional maps of delay and rotation measure, which are not orthogonal axes, but we're hoping to be able to invert them to create pseudo-orthogonal axes, where we can apply filters that are isolated to the delays that we know emission can come from on the sky, which we already are throwing out. But then also using this rotation measure synthesis to pull in the side lobes of those out of the rotation measure 0 EOR signal that we'd like to access. So yeah, so we can get order of magnitude suppressions. It's an open question of whether we can get that last order of magnitude. But it'll be close. I think it's pretty exciting that we're close.
We have time for one last quick question if anyone has one. Okay, in which case we're going to be taking power